jumped into what are called conic sections. I did conic sections after quadratics because conic sections actually, you complete the square pretty much non-stop in those. So I thought it was a pretty decent relationship between why do you do the square and why do you do this. But then I realized that after we do the conic stuff, we jump right back to polynomials, which goes back to factoring. So I decided to switch it a little bit and go into, which is weird, we're going right into the middle of chapter 6. Then we'll backtrack to the beginning of 6, and then finish the rest of 6. My hope is that we'll be able to get back to the conic stuff probably by the end of the semester. It usually takes about 3 to 4 days to get through it anyway, so it's not that it's a really long unit, but I figured since we've been working through all this factoring stuff, it wouldn't be a bad idea to just go right back to the factoring from where we were at. So, we'll see how it goes. It might work, it might not, whatever. You don't know until you try. So this kind of goes back to what we were doing last chapter. If I wanted to factor something, and let's do these one at a time here. If I wanted to factor 4x squared minus the 24x, what do you do first?
Divide by 4x.
Yeah. Divide by the 4x. Oops. And by dividing up by the 4x, what are you doing? What do you like? Well, yeah, but what is that called? What is it called?
Removing the greatest common factor.
Yeah, it's the GCF. You take the GCF out. Right? So if you take the GCF out, what are you left with?
X minus 6.
Okay. Now, this was just a factor problem because there is no equal 0. If this was an equal 0, where would your zeros be located at? 0 and 6. Very good, very good, very good. So, obviously, this isn't anything crazy from what we've done before. You've seen this, you've done this, and so on. What was different with one like this, though? What did you have to do? Multiply your ends, your tails, if you will, and then add to the middle. So when you did that, you'd get, what, negative 42 to get to 11. Right? So we have to figure out what are two terms that multiply together to get negative 42, but when they add together, they're positive. Well, that tells you one thing about it. The larger of the two has to be the positive value. Okay. So we know that the shortcut way of going through these things is that we know it's 2 and 21, but that doesn't get me anywhere near 11. So I just start checking other values. Okay. I go to 3, I get 3 and 14. Okay. So when you get those two, which one of those has to be the negative value? 3. The 3 has to be the negative because you want it to add to a positive. Okay. If it was add to a negative, it would have been the other way around. All right. So what we did is that we took our trinomial and we turned it into a 4-term sequence. And then what did we do whenever we had 4 terms? What did we always do? Factor it via grouping. Okay. So we factored this via grouping. We took the GCF out. Again, the GCF is pretty easy. It's 2x minus 3. GCF here was a positive 7. You got a 2x minus 3. Did you guys know that whenever I asked you, are these two things the same thing? And we were like, oh yeah, they are. And I said, that's a good sign. Well, technically what we're doing when we write that down, that's the GCF of these two terms. They have both, these guys have, the 7 has a 2x minus 3, the x has a 2x minus 3. I can factor that out. And I'm left with x plus 7. Technically what you're doing is you're taking the GCF again. We just never say it. Okay? Not at the end of the book you see that or not, it's just how that works. Right? So again, at this point, there's no equal 0. We just have our factored terms and we were done. Right? So far so good-ish? Now, what happens when we got to here? What were the questions that we asked? Perfect squares. Remember what that was called? This might ring a bell. What is what? Very good. The reason I was saying this is going to ring a bell is remember we'd asked, is the first term a perfect square? Is the last term a perfect square? Is that a subtraction symbol? If you answered yes to all three things, then you had the difference of squares. The difference comes in because it's a subtraction symbol. And the way that we factored this, what was the square root of 4x squared? 2x. What's the square root of 81? 9. So it's 2x and 9 on both sides, and we just have all three sides. Okay. It didn't matter which one came first. All right. What's going to be different today is that we're going to start talking about polynomials. Polynomials are, that's just a quadratic, because what's the degree? 2. When you have a polynomials, you know what polynomial stands for? Multiple nomials, yeah. Poly is many, nomials is just, like you have a monomial, 4x squared is a monomial, 81 is a monomial. Anything that's put together with multiplication is a monomial. Polynomial is just a whole bunch of them put together with addition and subtraction. So, for example, if I have x to the 5th plus 4x to the 4th minus 3x squared plus 2, that is a polynomial. Do you guys remember the difference between ascending and descending order? We did that in algebra 1, probably. When you had ascending or descending order, when you're talking about descending order, you always put the highest degree polynomial first, and then you work your way down in order. So when you did descending order, that was the only order you should have ever learned, because ascending order is never used, ever, like by anybody, ever. So there's no reason why they had to teach you it. So I'm sorry you got wasted some of your time. What's the degree of the highest power here? 5. So this is technically called a 5th degree polynomial. This, whatever this value here, this, I'll call it a to the n. This nth term, it's an nth term polynomial. It's a 5th degree polynomial. So it's an nth degree. Sorry, I didn't mean the right term there. Degree. We've been dealing with quadratics, which were 2nd degree. Okay. We had 2nd degree polynomials, we have 3rd degree polynomials, 4th degree polynomials, and so on and so on. When you had go back to your 2nd degree polynomials or quadratics, how many terms could you have in a quadratic? Have you ever had 4 in a quadratic? Yeah, at most you'd ever have was 3. You'd have a difference of squares, you'd have a square term, you'd have no x value, but then you'd have a constant. So what happens here in any nth degree polynomial, you can have up to 1 extra. You have n plus 1 terms within the polynomial. Doesn't mean it always is there. That's why I like to go back to difference of squares. Difference of squares is a 2nd degree polynomial which can have 3 terms in the sequence, but in that case only has 2. It only has 2 terms to it. This is a 5th degree polynomial, which means it can have a 5th, 4th, 3rd, squared, linear, and a constant, which means how many terms could it have in its sequence? It could have 6. Okay? A 4th degree polynomial can have how many terms in the sequence? 5. That's how this works. Okay? There are certain little subtle rules that will start to show up with the nth degree of the polynomial as we go through this unit. Okay? Because I don't want to give away too much of it, but it's kind of an important thing. It's kind of like why you were able to solve for x and get an answer. Kind of like why algebras is this unit. Reminds me. Hold your excitement. Jeez. God bless it. This is the worst. Okay? So far so decent-ish? Alright. Now, here's where things start to get a little weird-ish. when we had what was called the difference of squares, and we had a generic rule, we had a squared minus b squared. If I factored that out, our two terms were what and what? If I leave it in terms of a's and b's. Yeah, it was the square root of the a plus the square root of the b. It was the square root of the a minus the square root of b. Now we're going to get what are called sums. Oh, I'm sorry. Could this ever work? Was that factorable? You can't factor it. Could you find the zeros in it, though?
Yeah.
Yes, they're just imaginary zeros. Okay? They're not factorable, but you can still find zeros off of it. There's nothing called a sum of squares. But there is a thing called the sum of cubes.
Boy, it's time.
We're going to start talking about how to factor we're not hiring somebody. We're talking about how to factor higher degree polynomials today. It's really not. Okay? Now, do you guys know how to check for perfect cube, how to do a cube root in the calculator?
Well,
You hit math 4. Then you gotta use it.
yeah, I just think that says root or something.
Yeah, x power or the x root. That works too.
Yeah, and the root x.
Yeah. So in this case here, a lot of these numbers are going to be really easy to work with. There's really not much that's going to be tough. You usually are talking about perfect cubes because they get large real fast. More often than not, they don't get any larger than 6 cubes, which is 216. They don't get much bigger than that. They work out rather cleanly. So if I type in the calculator the cube root of 8, what do you get? 2. So what do you think the cube root of x cubed is?
2. X.
X. Remember, what's the square root of x squared?
X.
X. The cube root of x cubed is x. What's the fourth root of x to the fourth?
X.
So whenever you take the nth root of something to that nth power, it's just whatever the variable is. Okay? Those powers, those roots, undo one another. Now, what happens though is that these there are going to be patterns for sum, and there's going to be a pattern for a difference. Before, we weren't able to do a sum of squares because it didn't work. It wasn't factorable. But when we're dealing with cube roots, think of the third power, there will be, it will allow us to do these things. And there's two patterns that exist. I'm going to come back to this one. If you have a sum of cubes, I'm going to write out in terms of a's and b's again. And then I'm going to use my example of x cubed plus 8 as my what's going to happen. All right? So what happens here is the first thing we do is that this is going to break it into 2 bits. One of them is going to be a binomial, and the other one's going to be a trinomial, which means the first thing in parentheses is going to have 2 terms. The second thing in parentheses is going to have 3 terms. This works for both sums and differences, same thing. Now, excuse me, what's the cube root of a cubed? A. What's the cube root of b cubed? B. Was this a plus or a minus sign?
Plus.
All right, so far? All right, so I'm going to match that down here. What's the cube root of x cubed? What's the cube root of 8?
2.
Was that a plus sign or a minus sign?
Plus.
So far, so good? Okay. In the trinomial, then, it's that first term squared. A squared equals a squared, right? So what's my a value here? My a value is x, isn't it?
Yeah.
What's x squared? X squared. All right. Now, the last term is always going to be b squared. What was our b value here? It's 2. Remember, this is your a and your b. Okay, this is your a, this is your b. What's b squared?
4. Okay? In the middle, it's always going to be a times b, and it's always going to be the opposite sign of what you start with. Okay? So this becomes 2x. That's how you do a sum of cubes. It's a plus b, and then the trinomial is a squared minus ab and b squared. The difference looks exactly the same. The difference of cubes looks, this is not moving. There. The difference of cubes looks exactly the same. It's always the same sign to start. A squared, opposite sign, and it's always positive at the end. Okay? The only sign that changes is this is when you get to the trinomial. That's when it becomes the opposite. Okay? So if I do a difference of cubes, let's use x cubed again. We'll do minus 125. 125, what's the cube root of 125? Take a guess. 5. It's got to be 5. Okay? So you get x minus 5. The trinomial then, well, it's this first one squared. It ends the last one squared. And then in the middle, is that a minus or a plus sign that I just wrote? Over here. Minus, right? So now I write a plus. 5 times x. Yes, sir. Yes, sir. The last one will always be plus. Last one's always plus. That never changes. It's always the same change positive. Same change positive, want to think of it that way. So if we have, what was it? A cubed plus b cubed, a plus b, a squared minus ab plus b squared. It's a cubed minus, same sign, change it, always positive. Okay? And that's how it would work. One way that you can always double check yourself here is, what is 2 times 4? Is it positive or negative? Positive. Okay, that's a good sign that you have positive 8. What's negative 5 times positive 25? Okay. That's how it works itself backwards and forwards. All right. Bless you. So, jump right to the fun. Write this as 16x to the 5th. And one of the things I want to start thinking about is whenever I see 2 terms, in case I have 2 terms, I always want to start thinking, can I get some, difference of squares or sum or differences of cubes out of it? I always try to think of that when I'm factoring. In this example here, since there are 2 terms, your first rule of factoring is to always do what? Take out GCF. In terms of the variables, they both have an x squared in common. Are we okay with that? Yeah. If I take an x squared out of x to the 5th, how many x's are left? X to the 3rd. X to the 3rd. Okay, cool. I knew you guys knew that. I just wanted to make sure. I didn't want to jump too far through that. Now I have to figure out what am I going to do with the numbers. Well, if you know that you have an x cubed in here and it's going to be a difference, it's probably forcing you to get to a perfect cube. So, in your head, you start thinking, all right, 16, what's a perfect cube that goes into 16? 4. You guys are thinking squares still. 16 is divisible by 8, isn't it? Yeah. 8's a perfect cube, right? So what we're doing here is we're trying to make this into, I want to take out a 2, and I have 8x cubed. minus 125. Okay. Your GCF in this case was just 2. Okay. You could try 4, but 4 wouldn't go into 250. You could try 8, but 8's not going to go into 250. The only thing that went into 250 and 16 was 2. All right. It forces you into the different cubes. So there's no equal 0 here, is there? So this 2x squared's got to come along for the ride. I know I'm going to have a trinomial and a binomial to multiply out. So 8x cubed. What's the cube root of 8? What's the cube root of x cubed? X. So the cube root of 8x cubed would be 2x. Cube root of 125? 5. And remember, this sign stays the same. Now I square that first term. When I square that first term, I have to square the 2 and the x. You get 4x squared. What do I do with my next sign? Flip it next, change the sign to whatever the other sign is. So it's going to be positive. And then I just multiply these two together. So 2x times 5 is 10x. And then the last one is always positive. Oops, grab my x, sorry. What's 5 squared? That's how that works. Factoring higher degree, higher degree polynomials. Okay? Yes, sir.
The A, B part, we're making 10x, the center of the second part. The A and B values is 2x and
Yes, sir.
5.
Yep.
All right.
Yep.
So we ended up with a negative 10x, but then
you always change, think of it, don't worry about the negative. Think about it this way, your A value is 2x, your B value is 5. Yeah, don't disregard the sign. So it's just a squared plus AB plus B squared. Okay? Not too bad, is it? It gets a little get used to. Just takes a little getting used to. Okay? Oops, did that one. But let's try a different one. What's the degree of this polynomial?
3.
It's a third degree polynomial, which means up how many terms could it have in its sequence? 4. It's always one more than the degree. Okay? It's always one more than the degree. It can have that many terms in the sequence. When you see 4 terms, a dead giveaway of what to try and do, group it. Yeah, you want to try and group it. You're right, binomials, you try to split into binomials. Okay? You always put it, make sure it's in descending order, and you try to see if you can factor it via grouping, which is something you guys have all done. It doesn't matter that you have a higher degree first term. You're still doing GCFs. So if I group those two, what does x cubed and a negative 2x squared have in common? X squared. And then I want with x minus 2. Okay. My third term in this case is a negative, which means what should I do with it? Yeah, remember how we always say do that so you don't forget about it? So now you have a 9 and an 18. What do those two have in common? They have the 9, and you're right, take out the negative 9 because it's forcing you to do that. And I have x minus 2. Once again, are those two things in parentheses the same? Yes. Yeah. So we write it down. X minus 2. And what's left?
X squared minus 9.
X squared minus 9. Oops. X squared minus 9. Can I factor anything any further?
Yes.
Where? Yeah, the x squared and minus 9. That's the difference in squares, isn't it? Yep. So your final fully factored form, x minus 2, x plus 3, x minus 3. Does it matter the order in which you put those three things?
Nope.
Nope. Doesn't matter at all. Now, if I wanted to check my work, I'd have to FOIL all that together. I'd have to multiply the first two together, then I'd have to distribute to the last one. It's kind of ugly. It works. Or, at some point in time, you know you have to get what for your y-intercept? 18 has to be your y-intercept. Why is 18 your y-intercept, guys? It doesn't have an x is a really easy way of thinking about it, because if I substitute 0 in for x, you get 0 minus 0 minus 0 plus 18. Otherwise known as 18. Okay? So your y-intercept is always the constant in one of these. Whenever there's a constant, no matter what your polynomial is, that's always your y-intercept. That will never change. So what's negative 2 times positive 3? What's negative 6 times negative 3? Bless you. It's positive 18, isn't it? Where am I getting those values from? Negative 2 times positive 3 times negative 3. It's a nice, easy way for you to check if at least your constant is correct. And if that constant is correct, you're probably doing it correct. You're probably doing it the right way.
Wait, did you say that again?
It again.
Well, you did say it again. But can you say what the whole constant thing was?
Okay, so you agree that your y-intercept is 18.
Yes.
To get to that, it means it can't be multiplied by anything with values of x's. So in here, the three parts that don't have the x's are the negative 2, positive 3, and the negative 3. What's the negative?
So you can multiply them all together and you'll get that constant.
You should.
Or you should get.
Yep. You should be able to. You should get that.
Well,
You don't? You
You
do.
did something wrong.
Yes. Well, speak for yourself, you idiot. I just screw up. Yes, sir. Yep. You'll see that a lot. Okay? You'll see that a lot. Okay? Try this one. 3x cubed plus 7x minus 12x minus 28. I don't want to do anything equals 0 today. I'm going to leave that out for now. Okay? I don't want to worry about anything with zeros for today.
Forgot the square.
7x squared.
Oh, yes. Sorry, 7x squared. Thank you. I was too busy trying to move stuff around for that, so you didn't have to worry about zeros. Because if you have to worry about zeros, then you just got to do one more step, don't you? All right. So 3x cubed plus 7x squared minus 12x minus 28. You've got 4 terms in your third degree polynomial. Any and every time you see 4 terms, no matter what the degrees are, I always want you guys to try and factor via grouping. It's kind of, like I said, it's kind of a dead giveaway of what to do. So if you try that, what's the GCF of that first group? X squared. You get 3x plus 7. Bring my negative in. 12x or 12 and a 28 gives me what? 4. But I got to bring out the minus 4. And lo and behold, you got the same thing in the parentheses. And a difference of squares. What am I going to do with my difference of squares? Yes, ma'am. Yep, and what do you get for your final 3 terms? Good. 3x plus 7, x plus 2, x minus 2. And again, it does not matter the order in which you put that, it's going to work out just fine. Where was our y-intercept of this problem?
Negative 28.
Negative 28. So, what's positive 7 times positive 2? 14 times negative 2.
Negative 28. Actually, I want to ask a quick question. You know how we FOIL for the regular things? How do you do that with these? Do you just multiply the first 2 terms by the
Yeah, you can do that.
terms behind them?
If I was gonna FOIL this all out to check it, I would do these 2 first because I know that that's the difference of squares, and then I get 3x plus 7 times x squared minus 4, and then I would FOIL. So you can break it into FOIL those 2 together and then distribute it in the third. Normally, we don't really need to go backwards that much, but that is one way of doing it. It's just a big distributed property problem. You're just doing it in separate stages.
All right, so you could think of the back part as one distributed property,
Yep.
and then
Or how about this?
once you've gotten that into one part, you can do it with the first part.
What's 2 times 3?
It's 6,
Times 4.
24.
What's 3 times 4?
12.
Times 2.
Wait, 3 times 4 times 2?
Yeah.
That's 24.
What's 2 times 4?
That's 8.
Times 3.
2 times 4. Wait, 8 times 3 is 24.
Do the order in which you did any of that matter?
No.
It doesn't matter what polynomials.
All right. Just want to make sure I don't multiply something by itself or.
Yeah, no, that's the only thing I've worried about. Okay. Yes, sir. What if it's x squared plus 4? Then you can't go any further. Then, because here, if this was a plus 4, you can't factor that anymore. So you would just stop. If this was equal 0, you can do something. But for us right now, we're just factoring. We're not worried about that. All right. Yes, sir.
Is the x squared plus 4, is that a factorable thing, or we have to get to something else before we can do it, or is that just something we can factor?
We don't factor that. We use that if we're finding zeros. Because it'd just be imaginary zeros. It's just imaginary zeros. And this all comes back to why this is working when we start looking at the graphs. Because if you have imaginary zeros, where do they occur? Not on the x-axis. They occur above or below the axis. Where do zeros occur?
On the x-axis.
On the axis. So we can figure out where zeros are going to occur, but we need to figure out what direction they're coming from. And that's where we worry about factoring first, figuring out where our zeros go, because we know how to do zeros, we know how to plot zeros, we know where imaginary may or may not go. We just learn then what is the graph going to look like after we get this far. So we're using stuff that you can do. All right, it's a little bit different how to word stuff. Let's try this one, and we'll go to the other one. We're running out of too much time. 81x to the 4th minus 16. It's got two terms, doesn't it? Are they perfect squares? What's the square root of 81? 9. What's the square root of x to the 4th? X squared. Remember, that means x to the 4th is created by, if you want to take the square root of that, you're trying to think of what are two variables you multiply together with the exponent to get you to x to the 4th. Whenever you multiply variables together, all you're doing is you're always adding exponents. So x squared times x squared gives you x to the 4th. Okay. So is this a perfect square? Is this a perfect square?
Yes.
Is this a subtraction symbol?
Yes.
Which means you can create a difference of squares. What's the square root of 81x to the 4th?
9x squared.
All right. What's the square root of 16?
4.
And what do I do with the signs in between?
Plus and minus.
Plus and minus. Oh, wait a second. Another difference of squares.
Whoa.
All right. 9x. Should be so crazy. The 9x squared plus 4 just rewrites because it can't get factored any further because of the plus sign. But 9x squared. What's that? No! You cannot just square root it. That is not. It's not how that works. You can't do that. So hopefully you did not do that yesterday, because I know people were doing that, and hopefully it wasn't you. Yeah, I remember that. Okay. You cannot do that. All right. At this point, we're done. No, what?
You could go farther and rewrite 9x squared plus 4 is 3x plus minus 2y.
We're not. I'm not going to factor that. We're not going to factor two imaginary. What we'll do is we'll get zeros that are imaginary, but we're not going to factor it out that way. Okay, so you don't have to worry about that. All right. Now the other one's a little bit different, and I want to put this on a clean. I think I have it on the next one here. Yes. 4x to the 6th minus 20x to the 4th plus 24x squared. And this is kind of the weird one that will show up from time to time, but yet it's probably the easiest. Okay. Now, no matter what's always your first rule of factoring? What's our GCF here, guys?
4x squared.
So if I factor out the 4x squared, how many x to what power am I left with? X to the 4th, okay. Minus 5x to the 2nd. And then plus 6. We okay with that?
Yes.
Take a look at the degrees inside the trinomial. 4, 2, nothing. Okay? Ben, stay on the phone. I know you can do it. You've been staring at it the entire time we've been here today, except for the time you yell at numbers. Move away. Okay? It is true. Again, notice you have x to the fourth, x squared, and nothing. Now, when you had x squared, I'm trying to think of one in my head real quick. Minus 4 minus 2. Isn't this x squared x in a whole number? So when you factored this, x squared minus 6x plus 8, what were your two terms? It was, you drop the degree for here and here, because if you multiply those two together, you get x squared, right? Now, what times what's positive 8, you have to get negative 6. Negative 4 and negative 2, okay? What's different here? Nothing. You treat it the same way. Instead of it being instead of being like x minus 4, this would have been, if this was a fourth and this was a 2, this would be x squared. Because when you FOIL that out, what's x squared times x squared? X to the 4. X squared times negative 2 is negative 2x squared. Plus negative 4x squared gives you negative 6x squared. Whenever you have a trinomial, no matter what, whenever you have a trinomial that is going in descending order, where your degrees go 4, 2, nothing, 6, 3, nothing, 8, 4, nothing. If they're being cut in half between the first two and then it goes to a 0 degree, which is just a constant, this always works. You always treat it like you would any other regular, boring trinomial with two terms. What times what's positive 6, you add together get negative 5. Negative 6 and negative 6 and positive 1 would give you negative 6. Two things you multiply together to get a positive, and when you add them are negative, both of them have to be negative. Negative 2, negative 3, but here it's going to be just x squared. That's the only difference. You treat it like you would the exact same way. Okay? Now, since I'm factoring, one second. Since I'm factoring this, can I go any further? No. What's your question?
What happens if x is x?
If it was like x to the 5th and then x squared and the 6th, we can't do that yet. We will be able to, but not yet. Not for right now. No, because watch what happens. And this, there's a little weird, so in math, most of the time half the stuff we do is made up. Did you guys know that? I mean, we have imaginary numbers for Christ's sake. For Christ's sake, sorry, for Christ's sake. Excuse me, sorry, misspoke there. For creep's sake. So we have imaginary numbers. They had to make stuff up to make things work. So this looks kind of ugly, right?
Yes.
So in math, what we do is we do this. We use this little thing called U substitution. U substitution is used in math all the time when things look like crap and you want them to look clean. I'm going to let U equal x squared in this part here. So anywhere I see an x squared, what am I going to substitute in? U. So I have, this is x squared squared, isn't it? So it's U squared minus 5U plus 6, which gives you U minus 2, U minus 3, but what was U? See where you're going with that, but no. You can, but it can get kind of messy. We use this U substitution. You'll see this maybe, I think I use it maybe 3 or 4 times throughout this school year. You see it a little bit more in pre-calc, and then you see it a lot more in calc. We use this trick of what's called U substitution to make something that, in order to take something that looks kind of weird and crappy looking, and break it down into something that looks pretty easy. We're we're taking the complexity out of it. You have to just trust me that it's a weird thing and that we kind of do to help explain complex things. If it confuses, and a lot of people get like that.
Because we're mathematicians.
Actually, my answer is most because I just said it. So I got it.
But the idea is that it has to make sense. So you're still making up a rule, but the rule has to work. Yes. Yes, sir.
I just realized you should have said the Russian axis for this one. It's the Russian nesting dolls of math equations.
Right, yeah, I didn't do that one. It breaks down to many parts. What?
Oh God.
Igor comes, but it's gonna get, we come back from that. I wear a flowered shirt, and I choose to wear a striped suit with flowered shirt.
Oh no.
Why, what's up?
Love Murphy.
Things have to make sense.
What's that?
Things have to make sense. We have imaginary numbers. It's just they act like numbers. If they didn't act like numbers, we wouldn't have made them up.
That's true. And that's just one of those weird things. We'll probably use the U substitution again. Forget one.
Wait, does that
You don't have to use it, no. It's just another way of showing why this works. Then you just do it off of this. If you remember the rule, if you remember the trick, hey guys, if you remember the trick that it's, you know, x to the fourth x squared, if you see the powers going down by half and the last one has a zero, and it has no variable, just follow the same rule like you would have tried. Like I said, it looks really weird for something that's really easy. If you don't want to use substitution, don't worry about it. Pay no attention. This never existed. You never saw me talk about it. We never did it. It's gone. What's that? You can use it if you want. It's fine. Work through these, please. Their PDF is posted. I think there's like 12. All right. This shouldn't be so bad. These should be relatively straightforward. You're not finding any zeros today at all. We'll talk about finding zeros and how do they plot them. What is that going to look like tomorrow? Because what we'll wind up doing tomorrow is we'll start plotting zeros. We'll start plotting y-intercepts and trying to figure out what might be going on towards the end. Okay? Yeah, like I said, if you don't want to use the U substitution is another way to show it.